Hey guys, it's Andre from High Performance Academy. Welcome along to another one of our weekly webinars. Now, got a fair bit to get through today. We've had a fairly busy week. Not all of the things that went on in the last week have been great, as we'll find out. But had a little bit of racing over the weekend, and I'm going to get you up to date on that. And for those who have been following us for a while, I also wanted to just do a bit of an update on where we are at with our drive shafts, or actually our axles in the back of our Toyota 86 race car. Those who have been following will know that we've been having quite a bit of trouble with the axles not quite being right. The Toyota 86, for those who are unaware, let's just jump quickly across to my laptop screen. This is the engine bay here. It is powered by a 1UZFE Toyota 4-litre V8. It is a built motor. It is around about 450 flywheel horsepower there or thereabouts, just to about 8,700 RPM. Understandably, a little bit more than the stock 200 horsepower that the standard FA20 produces. So one of the issues, of course, is maintaining drivetrain strength with that sort of power. We've fixed the drivetrain issues in terms of gearbox strength because we are running a TTI 6-speed sequential gearbox. In terms of strength of the gearbox, obviously that's absolutely fine. These are rated up to around about 700 pound-foot of torque, so definitely a little bit in excess of where we are at the moment, being well proven with some very heavy V8 powered circuit cars, much more powerful and heavier than ours. So gearbox should be absolutely fine other than driver abuse. We are still running the stock Toyota differential, and at this point it's actually been quite reliable. We are running a Cusco 1.5 way LSD, and we've swapped to a 4.556 final drive, so slightly shorter final drive gearing than stock. Basically that gets us, with the 17-inch wheel and tyre package that we run on it, 8,800 RPM in 6th gear is around about 248 kilometres an hour, which just coincides with being the fastest speed that we're likely to see on our New Zealand track. So pretty well geared there. So that's all been pretty good. We've got the usual oil coolers on gearbox and differential, considering we are competing in endurance races here. So that makes sure that the temperatures will stay under control. The issue that we've been constantly battling for the whole season is with our axle strength. Now, when we purchased the car, and you'll be aware that we didn't actually build this car ourselves, we sort of got involved with the customer who owned the car, and we got involved with the electronics and the tuning, and basically it got to a point where he wanted to get rid of the car, and was pretty much a good combination for us to carry on the development with. So that's how we ended up inheriting the project, and we've sort of developed a little bit further. When we took ownership of the car, it had a set of Driveshaft shop. Depending where you look, I think they're either rated at 600 horsepower or 800 horsepower. Basically, their entry-level axle upgrade, and that's what we had in the car when we purchased it. It had been used a little bit, and we took it and did a 1-hour endurance race, and straight away basically rinsed the two out of CVs. I think that was just down, I'm struggling to actually remember the exact details on that. I think that was actually just down more to the grease that we're running, not being able to handle the temperatures we see in an endurance race. Anyway, we thought that the obvious upgrade, considering we were aiming to make more power over time with the car, was to jump up to Driveshaft Shop's 1,000 horsepower axles. So we placed an order for those. They are made to order, so it took a while to get them in. Placed them in the car thinking that that was going to fix all of our issues. Couldn't be further from the truth. Now, the 1,000 horsepower axles, part of the strength improvement is that they actually run a larger spline in the outer CV, and of course to do that they also run a larger wheel bearing with a larger internal spline. That's all bolted, and it's actually relatively quick and easy to change over. And we placed those axles in the car basically the first time we went to the track, did a handful of laps, and ended up with the inner CVs popping out of the LSD centre. Obviously not ideal. So we battled with this off and on without trying to rehash for those who have been listening to this for the last few weeks. We battled this off and on for our entire endurance racing championship, all 3 rounds, reverting to stock axles because we couldn't keep the 1,000 horsepower axles in the differential. Now, at the time we thought this was a little bit strange. Basically the axles, in our opinion, from what we could see, were basically just too short, and what happened is while they would click into the LSD centre, there was so much pressure being applied to them because they were at full extension that all it took was enough vibration or operation operating the car hard out on the track, and it could pop out of the retention on the diff. So we went back and forth with Driveshaft shop. Incredibly difficult to get answers out of them, which was really frustrating for us. I think we ended up chasing them up for around about 6 weeks with this issue. We're told that the problem was with the car, which we couldn't quite figure out, given that the geometry of the rear suspension was essentially stock standard. Basically, the only thing that was different was the car sat about 30 millimeters lower than stock. The other thing is that both the lower horsepower rated Driveshaft shop axles had been fined lengthwise, and of course the stock axles. So this sort of really didn't sit right with us. We went backwards and forwards, gave them all of the measurements that they asked for, and finally we got another couple of bars made that were longer based on the measurements that we had been asked for. Put them in the car, and again, if you've been following, a couple of weeks ago I went to the track just with some friends in the car, did about 10 laps at about 7/10 pace, and shattered the cage in the left outer CV. Obviously at this point getting a little bit frustrated with something that really shouldn't be that difficult to hold together. We contacted Driveshaft shop and were then told that the failure mode normally is a result of the axles being too long, which obviously at this point we're starting to get beyond frustrated. We also had a race meeting that was at that point less than 8 days away, and at that point basically Driveshaft shop stopped answering our emails and wouldn't reply when we rang them. So as a last ditch effort of frustration, I actually reached out on my personal Facebook page just trying to find someone who was able to actually answer my questions, where at this point we're about $4,000 deep in these axles and they don't work. So really frustrating scenario for us. And fortunately someone actually tagged the owner of Driveshaft shop. It's a really long story here, and I do actually feel a little bit for Frank, the owner of Driveshaft shop. He's sort of moved away from the commanding the whole business, and I think some of their customer service has suffered as a result. Anyway, in defense of Frank, he was actually pretty good to deal with, and within 24 hours he actually had a shipment of parts on the way. Belief was that the length of the axles actually was correct, and what he's done is he's upgraded us to a different type of outer CV, which hopefully should be stronger. Now unfortunately, despite him getting those parts away, the UPS shipment arrived the day we were leaving for the track, so we actually couldn't put those in. In the meantime, we had no option but to purchase locally another set of second-hand 800 horsepower Driveshaft shop axles, so they went in the car. So basically the saga continues. And I think it's something that has been a bit of an eye-opener, because we really would have considered this to be something that should be pretty straightforward. As part of that post that I put on my personal Facebook as well, actually had a couple of other people with GT86s mention that they're running the 1,000 horsepower axles and they were also too short or popped out. So it looks like the problem maybe isn't in our car, but anyway, we'll get to the bottom of that and let you know how we get on. Now, good news is that the axles on the race weekend were perfect. We had absolutely no issues with those. Instead, we broke something much more expensive. This is what happens when, unfortunately, I couldn't attend this race meeting. I had a friend's stag do up in Wellington, so Ben and the team actually went to Teretonga and Invercargill to race on their own, and it didn't go well for them, unfortunately. Didn't go very well at all. So we'll just jump across to my laptop screen for a second and we'll show you a short video of what actually transpired. So this is about 8 minutes away from the end of a 1 hour endurance race. At this point, Ben notices some smoke out the back, obviously some flames underneath the car, and decides things aren't quite right. You can see that car also gets quite loose, surprisingly, with a lot of oil under the rear slicks. It's not that easy to drive. I just want to rewind a little bit because I just want to point out my personal favourite part here. So Ben's driving a straight line here. Obviously this here, this is not good. If you ever see this in your rear view or side mirrors, that is a sign that something is severely wrong. So Ben obviously notices that, along with a lack of a power. And you can see here a little glance from Ben out to the rear view mirror, which is where our GoPro is. Obviously heard something. Is everything okay? Yeah, no problems here. We'll just keep on going. So that was unfortunately the end of our 4-litre 1UZFE V8. And at this point, what we've got here, I think I've got part of it. This is, I think, a little bit of the piston on number 1 cylinder. we'll just chuck that under our overhead camera here. Got a few other bits for the rest of our webinar today. As you can see, not a whole lot left of it. I've coined the term here secondary forging because this has been formed under immense heat and pressure inside of the cylinder by what was left of the piston, the valves and the conrod. So obviously not what we want as an end result. And obviously this is working out quite nicely for us today because our webinar that we're going to follow on to here is about failure analysis. So it really couldn't have come at a better time, although we also didn't really need any more work to do on this car. So it really comes down to what actually has gone on, finding out the reason for this failure and figuring it all out. Now, what I'm going to do, we'll jump over to my laptop screen, and the engine was giving us a few clues that maybe something wasn't quite right. So this is the dyno screen. We dynoed it, we try and dyno the engine before every single race meeting. It lets us stay on top of everything, making sure that everything is as it should be, so we don't get to the track and find that we've got some problems or some surprises that we weren't expecting. In particular, this was actually quite worthwhile on the Friday, the Thursday, when we dynoed it. Straight away we actually found that we had a misfire, so a new set of plugs and another brand new coil went into that, fixed that up, so that would have saved us a lot of time if we'd been at the track. Generally you'd end up chasing your tail probably for a couple of practice sessions with an issue like that, particularly if you don't have a lot of data. It can be quite tricky to diagnose where a misfire like that is coming from. So with that, with the individual bank lambda, we could straight away diagnose which bank of cylinders the misfire was coming from. And then by holding the engine under light load and then unplugging the coils individually on that bank of cylinders, we could then highlight which individual cylinder the issue was on. So it makes diagnosing really quick and easy. So it's just another point there. If you are racing competitively, it is always a good idea to frequently dyno test your car, even if not making tuning changes, just to keep it on track of where it is. And that really leads me to what we're seeing on the dyno screen here. So the best run we've got here is the blue run, 399.5 horsepower. That was after we raced the car at Teretonga last time. That is a little bit of an anomaly. The car normally produces about 384 to 386 horsepower at the wheels. The 400 horsepower run that we had there was with the front bar removed, and it gets a lot more air feed into the intake system. So 385 would probably be closer to our normal mark, but what we can see here is the red line, which was on Thursday before the race meeting, 365.6 horsepower. So it's pretty unusual for this engine because we have run it on the dyno so many times. It's always within a few horsepower of that 385 horsepower mark. So for it to be straight away 20 horsepower down, that's a significant issue and a bit of a red flag that something isn't right. Which you might say, well, why would you go to the track and race it? Well, fair enough, but what we have here is an engine that's still making 365 horsepower. There's no mechanical noises. There's no sign of any issue in the tune. So while, yes, it's definitely trying to tell us something, and hindsight is always 20/20, just given this particular dyno run, there is nothing to concrete say that the engine is about to fall to pieces. In particular here, I probably did 8 to 10 runs, making a few tiny changes here and there, and every single run was consistent, one on top of the other within a few horsepower. We also had an incredibly hot day while we were tuning it. So here we're right in the middle of summer in Queenstown. So sort of some of it we did put down to the heat of the day. Wouldn't account for 20 horsepower, but yeah, there you go. So that's why it's a good idea to take note of where your engine power is, and if it is trying to tell you something. So diagnosing what's gone on here. And again, we're going to be talking a little bit more about this during the actual webinar, but this is the side of number one cylinder, and you can see that there's not a lot left of it. Interestingly though, normally this would be, my gut feel would be that it's thrown a conrod out the side of the block. In this case, you can actually see that the conrod is largely intact, and so is the wrist pin here. We've still got the wrist pin through the connecting rod. So again, again, without the fact that the engine is still in the car, we haven't had the opportunity to get it out of the car to tear it down. At this stage, it does look like we've had a piston failure, which probably would be not unheard of. This isn't an engine that we've built, so again, this was built for the last owner by a race shop here in New Zealand that specialises in building 1UZ for stock car use. So they're a basic, relatively basic 4-litre stock car engine. They are limited in the compression for that class to, I think off the top of my head, 10-to-1 compression. So with this and the fact that they only produce around about 400 horsepower in the stock car class, 450, there isn't really a lot of need to go to an aftermarket forged piston. So they actually run with the stock Toyota cast piston. As you can see there from that photo, they do run an uprated H-beam connecting rod, and part of that is due to the fact that these run through, or this engine ran through to about 8800 RPM. So while we haven't got to the bottom of it yet, obviously the engine has done a full season of endurance racing. In between the endurance races themselves and the fact that each of those rounds has a full day of testing where we were averaging about 70 to 90 laps out on the tracks we were running at. The engine has had a lot of use, but of course we certainly wouldn't expect a catastrophic failure like that out of a season of racing either. So stay tuned, because once we actually get it apart, we'll hopefully have a better idea of what's going on there. So anyway, unfortunate way to end our season's racing, and basically while we were in the process of considering our options for a new engine for the car, this has kind of sped up that process. Where we were at with that engine is that, as I mentioned, it's around about the 450 flywheel horsepower mark, give or take, and we are in a class which is 3.5 litre engines and above, so we're quite outclassed by a few of the cars. Particularly there are two competitors in our class with LS7s producing 650 to 700 horsepower. There is another competitor joining the series next year with a turbocharged 2JZ that ends up in our class as well. Obviously not very difficult to make a lot of power from a turbo 2JZ. So we are a little bit outclassed, and what we want to do is get a little bit more power out of the engine. I say a little bit, but ultimately another 100 horsepower would be nice. We do need to balance this and be a little bit sensible with it, because we are a little restricted right now on the tyre width, or the slick width, that we can run. With this car, we've basically decided that we're not going to go to the trouble of wide bodying it at the moment. So Rocket Bunny kits or the like are out for the moment, so we really need to stick with what we can make fit under the guard. So it's important to try and balance the power and the amount of grip. There's no point going and adding another 200 or 300 horsepower to the car and make it an absolute weapon in a straight line. But if the car's undrivable and we've got more power than we can put to the track, it's actually going to make it really hard to drive, and particularly over a 1 hour race, that's going to end up being really tiring on the driver. So it's all about just trying to get a little bit more power without overpowering the existing chassis, and we think around that 100 horsepower mark should be the sweet spot. I doubt that that's going to have us class competitive on the top step of the podium, but we should be at least in the top 5, and that'll give us some cars to battle with, so we should be able to have a reasonable amount of fun anyway. So there you go, not exactly the end to the season that we were hoping for, but that is what happens sometimes in motorsport. Now, moving on, I just wanted to touch on, and this sort of again really goes along with today's webinar, I just wanted to touch on an Instagram that I put up for HPA quite a while ago, and we reposted it yesterday, so a few days ago, some time ago, I don't know. Anyway, if we jump across my laptop screen, this is one of the options that we used for head sealing on some of our 4G63 drag engines, and the reason I want to talk about this is when it comes to turbocharged engines, particularly when you're trying to make a lot of power with a high boost turbocharged engine, the head gasket integrity becomes one of the real limitations on how much power we can produce. Basically, as we add more boost, our cylinder pressure increases. We've got that cylinder pressure physically trying to separate the engine block from the cylinder head, and it doesn't take much flex there for a factory MLS style, or worse still, a composite style head gasket to fail and leak that cylinder cylinder pressure straight into the coolant jacket. So this ends up being pretty messy. You're going to end up doing a lot of damage to your engine, and ultimately can end up also putting water out under the tyres if you are still running a wet block. So there are a variety of options when it comes to head gasket sealing. I just want to talk about one that probably I don't think is that common or that well known about, and that is these aluminium bronze sealing rings. So that's what we can see here. So it's a rectangular ring that is then stepped down into an O-ring groove in the block. So it's actually locked down into the block. There is a machine groove in the top of the block. I think I've got another photo here. Yeah, there we go. So you can see the little square groove in the top of the block. So the base of these aluminium bronze sealing rings actually has, basically it's not rectangular, it's actually an L shape. So it sits down and locates into that groove. Now that's going to seal directly against the cylinder head, and what these do is, particularly under the heat of combustion, they expand, and when they expand they basically lock into the cylinder head and really help seal. They also provide the ability to have a little bit of flex in the cylinder head, which is something we can't really get away from. It's always going to be some amount of flex between the block and the cylinder head with massive cylinder pressures, but these will allow that flex without breaking that seal between the block and the cylinder head. Now that's all well and good. That covers the combustion pressure, which is our main consideration, but it doesn't really factor in the oil and water, which is the other aspect. And here you can see we've got this copper gasket, and copper gaskets are pretty common. They're used in the likes of Top Fuel and Top Alcohol, probably the most powerful engines in the world with Top Fuel in particular, but they are used in a particular way. The copper gasket is annealed, and then it is used in conjunction with a stainless steel wire O-ring that's placed in a groove in the cylinder head, and that wire O-ring protrudes quite a lot from the cylinder head. So when the cylinder head's bolted on, that O-ring will press down into the copper material, and it will deform that copper gasket down into a receiver groove, which is machined into the engine block. So basically it forms a nice tight lock between the engine block and the cylinder head. The problem with copper gaskets is they do a terrible job of sealing oil and water. Not an issue so much for Top Fuel drag engines, but definitely a problem for anything that you want to put on the street. Now that isn't really fixed with this particular setup here. We are still using the copper gasket, but this is just dummy assembled here. What we end up doing is using a sealant, which is a 3-bond sealant that's placed on both sides of that gasket before it is placed on the block for the final time, and that helps seal that oil and water. So it's not something you're going to be using on your everyday street car, but particularly when you get to a point where head gasket integrity is a really limiting factor, this is a good way of doing it. Now, just to give you some insight, there are a number of high-end race engine builders that are using this technique, the likes of Proline, which are well known for their Pro Mod turbocharged engines. Proline also doing, as I understand it, the engines for the likes of underground racing with their Lamborghini and Audi drag race programs, so pretty well proven at the highest ends of turbocharged drag engine performance. And now I have talked briefly about our newest venture with Nigel Petrie from Engineered to Slide fame, which is our ETS Motorsport Fabrication School. And I just want to remind you that if you are interested in branching out your knowledge a little bit from the engine building, engine tuning and wiring that we cover here at High Performance Academy, you want to get broader out into the general motorsport world, then motorsport fabrication is a really important skill to understand. So again, if we jump over to my laptop screen, we have got an ETS Fab Instagram account, and I'd really urge you to head along and give that a follow. Nigel's posting some really great content on there to expand your knowledge. So even if you're not interested in actually purchasing a fabrication course, that's absolutely fine. There's a lot of free information in these posts that will help you to expand your knowledge. In particular here, this is a photo that Nigel posted up of the way the exhaust system is supported here on an open wheel race car, and it's something that we often sort of overlook overlook or don't give too much consideration to is the way the heat affects the expansion of materials, particularly with the exhaust system obviously being very hot when the engine is running under high load. It's going to expand, and we need to account for that, particularly here we can see with the way the exhaust system is mounted and supported. We need to make sure that there is going to be the ability for the exhaust system to flex and expand. So again, if you're interested in learning a little bit more from Nigel, please make sure you follow the ETS Fab Instagram account. Speaking of other projects as well, if I can find it, we'll just head across to our RaceCraft sister company YouTube channel. And again, if you're not following that, please make sure you do. So this is one of the latest videos that we posted, which was when we visited Jodasport over in the UK. This was over the time that we visited the Goodwood Festival of Speed. So this is one of their Orica LMP2 race cars, runs in the World Endurance Championship Series, and one of the aspects we're looking at here, there are a few videos that we've actually shot on these cars covering different parts. One of the aspects we were covering off here was just the way the dampers work. So I'll just actually pause that for a second. So not a big surprise, we quite often see complex looking dampers on race cars of all sorts with a whole bunch of different adjustments. So we're talking about those adjustments within this video and finding out what they do. In particular, a lot of people who've got a bit of knowledge around suspension tuning will have probably heard of the terms low speed and high speed bump and rebound damping, and this allows the suspension or the damper to be tuned to suit the characteristics of the racetrack as well as the driver's preference. So low speed, for example, is how the car responds as the driver turns into a corner, so relatively low speed body movement. High speed movement is where the suspension is responding to bumps or irregularities in the racetrack. So that's all well and good, but what we do quite often see is a situation where the driver will need to run a curb or a ripple strip. And now we see that all the time in the likes of saloon car racing with a lot of suspension travel and cars that are generally sitting higher. If anyone watches the Australian Supercars Championship, we're quite often used to seeing these cars well and truly up on two wheels on the very large curbs that they put in purposely to slow the cars down on some of the street tracks. Now that's not going to work quite so well if you're running a LMP2 prototype car or the likes of an open wheel race car, a formula car. That's going to really upset the car and the balance, and basically normally it's going to shoot the car off the track backwards. There are certain areas though where in order to get a faster lap time, it may be inevitable that running over a certain section of curbing or ripple strip is essential to actually straighten out the track. So these dampers are built with what's referred to as a blow-off valve. So a little bit different to the normal terminology where we hear that term blow-off valve. This has nothing to do with releasing boost pressure. Basically what it is a valve inside of the damper that allows very rapid movement in response to running a curb like this. So this allows the driver to run over that curbing. The suspension will absorb that curb bump really quickly without upsetting the balance of the car. So if you want to learn a little bit more about that, head across to RaceCraft HQ's YouTube channel and make sure you subscribe while you're there. If you do have any questions on any of the RaceCraft HQ videos, please make sure you ask those and I'll be happy to answer them in there. Right, lastly, we are still running our HP Tuners giveaway. So if you are interested in winning an HP Tuners MPVI2 interface, off the top of my head, I think we're adding around $300 or $350 worth of universal credits to that as well, which should be enough to set you up to tune most of the supported vehicles. Then I'll get the team to drop a link in the chat that you can follow to get your name into that draw. I don't think that's got too long left to run, so you're probably going to have to move pretty quickly if you want to jump on that. We are also including in that a entry to purchase I I'll try and get the words out. You're not going to be purchasing anything. The winner of that package deal is going to also win a suite of our tuning packages. So our EFI Tuning Fundamentals course, our Understanding Airfield Ratio course, and of course our Practical Reflash Tuning course. I was just checking on that, which is why I got my tongue tied a little bit. There are 3 days left for that package to run. So if you are interested in getting in the draw, head across and make sure you do that. It is a great package. It's worth around $2,000 US. So get your name in the draw. You never know, you could be the lucky winner. And just to put your mind at rest as well, you don't have to be in New Zealand, you don't have to be in the US. Regardless where you are in the world, we will ship that to your door. All right, team, thanks for watching there. Give me a few moments and we will get started with today's webinar. Now, I will also actually mention before we get into the webinar, because we are dealing with much the same content here, engine failure analysis, I am going to reiterate some of what I've already talked about our 1UZFE failure. So sorry that I will have to be doubling up. All right, give us a second here.